Welcome back. This week we started looking at the idea of a time varying signal, right? So we saw that in the first week we were dealing only with a circuit like this, okay? And this was some voltage, there was a resistor here and you had a current I, and this was simply the related by V equal to IR. Now this voltage source that we are talking about was a DC source, right? That is a direct current source, in the sense it did not vary with time. So you take this and you simply plot this voltage as a function of time, right? V of t, and this was just fixed. So it did not matter when you made the measurement and whether you took an average measurement across time, all that did not matter. You would get the same value, and that's why we could use a voltmeter to make all the measurements. Now we have already seen that we need to deal with certain signals which are time varying in nature. For example, from the microphone, right, we saw that you had a signal something like this. When you speak, right, you would have a certain amplitude, a certain frequency, and effectively the voltage that is generated is now varying with time. Okay, so therefore we need to deal with such signals, and one very important signal that we need to deal with in electrical engineering is the sinusoidal signal. Okay, so the sinusoidal signal has a very specific form. The voltage that we generate can be written as VPP, okay, or I will say VP sine of omega naught t plus phi, okay, where VP is the peak voltage. Omega naught is the angular frequency, and phi is the phase. Okay, so let us first look at where we encountered these sinusoidal signals in electrical engineering first, right? So you remember the experiment that we did with the motor and the generator kind of thing. We got a sinusoidal thing. So the electromagnetic induction right, coil rotating in a magnetic field. Right, and the sinusoid came about because the coil was rotating at a fixed angular speed omega, and therefore the angle theta with respect to the magnetic field, right, the area vector with respect to the magnetic field gave you an omega t angle, and that's what gave you the cos omega t for the flux, and then you get the induced voltage also as a sine omega naught t term. Of course, we have also seen this in simple harmonic motion, right? Harmonic motion. Okay, so if you basically just take a very simple spring, right, and you have something here that is make it oscillate, or you take a simple pendulum, right, and you allow this to oscillate with some small displacement, then you would see that this is the displacement will be sinusoidal in nature, and so on, right? Now we have also encountered this in waves, okay, and we will come to this later, because when we talk of harmonics we have to talk about waves. So when you talk about, let's say, a string instrument or a wind instrument like a flute, right, then there are certain modes of oscillations that are allowed, okay, and these waves give you a certain sound, right, and that's how we hear music from a flute or a violin, for example. and you also will be dealing with harmonics there. That is, only certain frequencies are allowed in that particular wind column or in that particular string instrument, right? So we'll come to that a little later. So in any case, let's look at the the simplest case where I have my V of t is simply Vp sine of omega naught t, right? So let's plot this first of all and understand how this is going to look. Okay, so I am going to first look at this plot, which is going to go from and I will also assume omega naught is equal to 2 pi. Okay, so I am actually going to look at the simplest case is Vp sine of 2 pi t. Okay, so I am going to start with 0. Okay, it will be obviously 0, and when t equals, so when t equal to 0, V of 0 is obviously 0. When t equal to pi by 4, right, then we are going to look at the maximum value. So V of pi by 4 will be equal to Vp, right, because 2 pi by 4, no, t equal to 1 by 4, I am sorry, not pi by 4, right, t equal to 1 by 4, this will become sine pi by 2, it will become the maximum value. So if you look at t equal to 1 by 4, okay, this is 1 by 4, and then when I look at t equal to half, you are back to 0 because it's sine pi, right. So this is t equal to half, and then I have 3 by 4, and then I have 1. Okay, so the waveform is going to go up to a maximum value. It will then come down. No, this is not nice. Right? So this is how it is going to look approximately, okay? V of t. Now what happens beyond t equal to 1? It actually simply repeats, because the sine function, as you know, is a periodic function. So if I simply add 2 pi, right? So I can say V of t is equal to V of t plus 1, right, or t plus k, where k is an integer. Okay, and why is this? Because you just substitute this and see V of t plus k, when k is an integer, is Vp sine of 2 pi into t plus k. Obviously the 2 pi plus 2k pi will just vanish because it's it's circling back to 0 there. So it will simply become Vp sine of 2 pi into t, right? And what is this value here? This value is going to be Vp, and this value is going to be, if you look at here, it will be minus Vp. So the sinusoidal wave is contained between plus Vp and minus Vp, and it just repeats after 1 second actually. So if you look at this particular wave, it will just continue to do exactly the same thing. It will go like this, it will fall, then it will come down, right, it will just go all the way, it will keep repeating like this. So this will be 2, 3 and so on, right. So this time period here, right, for which the wave has unique values and after which it starts repeating, is called the time period. So this is t equal to 1 second in this case, okay, and I can define a frequency for this sine wave f naught equal to 1 by t, which is also equal to 1 hertz, in this particular example, right? So this is a sine wave with a time period of 1 second and a frequency of 1 hertz and an amplitude, right? Vp is essentially the amplitude of the sine wave, which goes all the way to a value of some Vp voltage, right? It could be 1 volt, 2 volt. In the case of the power supply that you have at home, if you remember, right, then that's going to be a much higher value. Okay, we'll come to that in some time. Okay, now how does this wave look if I am going to now look at Vp sine of omega naught t, okay, where omega naught is now 2 pi by t. So this is a wave with a time period equal to t, of angular frequency equal to omega naught, and your frequency is f naught is simply going to be 1 by t. Okay, so let's now plot this function here. Okay, v of t, and I'm going to look at different values of t here. Okay, so just as I looked at the case when it was 1 hertz, I will look at t by 4, okay, then t by 2, 3t by 4 and t, right. So exactly like what we had earlier, right. So remember, this is equivalent to Vp sine 2 pi by t into t. Okay. So therefore, if you now look at this value at t by 4, it will be 2 pi by t into t by 4, which is going to be pi by 2. So it will go to its maximum value here, and at 3t by 4 it will go to minus 1. So exactly this. Right, and then it is going to continue exactly like to the same way. It's a periodic signal, it will continue all the way to 2t, and this is obviously going to be what is this? This is going to be 3t by 2, right, and this amplitude will be Vp, this will be minus Vp. Okay. So now what we will do is we will look at this particular case where we have an alternating current, right. So this is known as an AC signal, okay, alternating current, which we can also apply across a resistor. Okay. So what we will do is we will go ahead and look at this particular source. An alternating current source is indicated by this symbol. Okay, and I am going to simply connect this across a resistor. So this is my V of t, okay, this is my R, and instantaneously you are going to have a current from this particular source, which is also a function of time. Okay, and I of t is going to be V of t by R. Okay, so if you look at I of t now, it's going to be Vp sine of omega naught t divided by R. So you could write this as Ip sine of omega naught t. Okay. Now this is an instantaneous current value. Okay. So similarly, you could also define an instantaneous power value, P of t, which is simply going to be, if you remember, it is just voltage into time, into current, sorry, into I of t, not small I of t, right? And now what I might be interested in is to see what the value of the, what is the net energy that has been delivered by this power source by delivering a current of I of t, right? So if you look at the power definition, if you remember, it is just rate of change of energy, okay? So therefore, if you want to look at the energy in one cycle, all you have to do is you have to integrate this from 0 to t for the instantaneous power into dt, okay? So you can now go ahead and solve this integral 0 to t v of t into I of t dt, right? And then you can simplify this and you will get Vp squared by R, okay, into 0 to t sine squared omega naught t dt. Remember, omega naught is equal to 2 pi by t, okay? So now I can write this sine squared omega naught t using trigonometric identities as 1 minus cos 2 omega naught t divided by 2, right? So therefore I can write this as Vp squared by R, okay, into integral 0 to t 1 minus cos 2 omega naught t by 2 into dt, okay? So this cos 2 omega naught t, right, is again going to be a periodic signal, right? So we will come to that a little later, but that is also periodic, but with half the time period, okay? So maybe we should look at that before we proceed, okay? So let us go ahead and let's just keep this equation as it is for now. And we will come back to this equation in a while. So we have now come across a new term, cos 2 omega naught t, right? So how is this function going to look as a function of time? Okay, this is time t, and let me call this some u of t, okay? I am going to simply assume that the amplitude is 1, okay? I am not going to worry about that amplitude term because it is a constant, it will come out of that integral, okay? So now when t equal to 0, u of 0 is simply going to be 1. So this is going to start at its highest value, which is 1, okay? And at what point will it come down to 0, right? It will come down to 0 when 2 omega naught t is going to be pi by 2, because cos pi by 2 is 0, right? So which means 2 into 2 pi by t into t equals pi by 2 implies t is simply going to be t is simply going to be t by 8. So at t by 8, you will see it coming down to 0. Then at t by 4, it will go back to minus 1, because then it will become cos pi, okay? So this wave will start like this, right? It will go and then it will come back here, t by 4 plus t by 8. So how much is that? That is 3t by 8, right? And then it will come down to t by 2, right? So this is what will happen, and this is how the cos function will look. So, so remember this periodicity, okay, is actually t by 2. Beyond this, the cos wave will repeat itself exactly like this, okay, coming down all the way like this, going up. So this will be another t by 2. So what we were looking at earlier, right, in this particular integral, right, let me just copy that. Okay, I am going to copy this now. Right, we wanted to solve this particular equation here, right, and this equation can now be split as Vp squared by 2 into integral 0 to t half dt minus integral 0 to t half cos of 2 omega naught t dt. Okay. So what we have here now is Vp squared by 2 into so Vp squared, oh no, I have removed the 2 out here, sorry. So this is just 1, this is also 1, right, into Vp squared by 2 into t minus Vp squared by 2 integral 0 to t, sorry, capital T cos of 2 omega naught t dt. Okay. So what we have now is we have an integral of cos 2 omega naught t dt, and what we see here, ultimately remember integration is just the area under the curve, okay, and if I have equal positive and negative area covered across the region of integration, then the answer will be 0. So here I can split this integral into 2 regions, right. This is region 1, and this is region 2. Now in both cases, it is the area is, you know, there is a positive term here, okay, these are my positive terms, and there is an equal and opposite negative term in this particular region here, okay. So therefore if you look at this integral, it has to be 0. So this integral will simply vanish and become 0, okay. So you can safely say that the energy delivered in one cycle is Vp squared by R into 1 by 2, okay. So effectively what we have now is the energy in one cycle is Vp squared by 2 into R, therefore the average power in one cycle is simply going to be division by T into this, right. So you can divide by this particular value, sorry, and oh, this is not 1 by 2, it is T by 2, yeah, T by 2, right. So if I simply divide by T, I will get Vp squared by 2 divided by R, okay. So now let me take you back to that particular experiment that we did with that heater, right. If you remember, we had a heater, okay, we had a heater element which was nothing but a resistor, okay, and in the first couple of lectures I derived it saying assume that this is a DC source, though in reality we were actually drawing current from an alternating current source from the main power supply, right. So that has, you know, was a very high voltage, high current power supply which was giving us a sinusoidal wave, but I said that in order to calculate the power, it is okay to make this approximation. And we said we used a voltmeter, we plugged it into the socket, and that voltmeter read 230 volts. 230 volts, right? And the resistance we measured was about 50 ohms. So if you did a wattage calculation, the power we got some V squared by R. Okay, this is let me call it V1. V1 squared by R was approximately 1 kilowatt. So how was this justified? It is perfectly justified because what the voltmeter read for us was actually this, effectively this quantity. Okay, so the voltmeter read out what is known as the root mean square voltage. Okay, so why is it called root mean square voltage? You just go back in this to this derivation. We basically took the square of the voltage, then we took the area, okay, and then we divided it by the time period here in order to get the average power, right? So this was the mean. So we did a square, we got a mean, and then we are taking a square root, okay, and to get that 230 volt. So what the root mean square actually reads is Vp by root 2, okay, and this was 230 volts that was read out by the voltmeter. So what does this mean? The current that actually is coming out, okay, from your supply, from your main power supply at home, is a sine wave of this form, okay. So remember, in this equation the time period has been removed. It doesn't matter whether it's a 1 hertz or 50 hertz, 1000 hertz, 1 megahertz, it doesn't matter. The average power is still the same, right? So the sine wave that is actually coming out of your supply at home is Vp equal to 230 into root 2 volts, and this is minus 230 into root 2 volts. So when you use this particular signal in order to heat that kettle that we had, which was just a resistor of 50 ohms, it was delivering an average current as if a DC source of 230 volt was actually driving current into it, okay, and that is why this root mean square voltage approximation was a very valid approximation, and we could still discuss it as if it were a DC source. So the time period has been removed from this, and therefore of course this is an additional fact which doesn't come out of the experiment we did, but this frequency, right, there is a time here, 1 by t in your mains is going to be 50 hertz. Right? So if you look at the time period, this will be about 20 milliseconds, right? So in the next lecture we will look at what is the meaning of a harmonic, and why we have to deal with the harmonics in electrical engineering as well.